There we go. Okay. I always hesitate before it starts rolling numbers. All right. We're on page 22 in your book. We just checked your homework from last night. Page 22, acceleration. There is no homework tonight, no homework questions, so all you got to do is watch the video. Okay? Okay, here we go. And read, of course. You always got to need to read it. Talking about acceleration, it starts off, it just talks about how a pitcher throws, the ball speeds up towards the batter, off the bat it goes, it's going, home run. But what it's getting to is, how many times did that ball change speed or end it, okay? The motion, okay? Actually more. Before landing, the ball went through several changes in motion, okay? It actually sped up in that pitcher's arm. And believe it or not, if you've ever watched, especially a professional baseball player, pitcher, now when he pitches, he'll take that long stride out because the power comes from the core, just like in any sport. But you watch his arm. His arm, I mean, that thing is whipping around because the faster the arm motion is, the more speed he can generate on that ball. So he actually, that arm whips around pretty fast. And when it leaves his hand, it's actually going, probably, if you got a guy that can throw 90 miles an hour as it crosses the plate, it's probably leaving his hand at 93, 94 miles an hour. And it slows down as it's actually approaching the plate. Okay, so if you got a guy throwing 101 miles an hour, it left his hand going even faster than that. Okay, that's how much speed that they can generate, though. But anyhow, so as he throws it, it actually starts to lose speed as it travels towards the batter, and then the ball. If we had a camera, could actually film, 50,000 frames per second or something, you would actually see that when it makes contact, the ball momentarily stops. Just that split second, it comes to a complete stop, and then it takes off in the other direction. So, and then of course, as gravity gets hold of it, even as it's going over the home run fence, gravity will pull it back down. So it changes directions motion quite a few times. Okay? So most example of motion involve similar changes. In fact, rarely does any object motion stay the same for very long. Okay? If you are a passenger in a car stopped at a red light, when the light changes to green, the driver steps on the acceleration. As a result, the car speeds up or accelerates. And in everyday language, okay, in layman terms, acceleration just means the process of speeding up. Okay? But acceleration has a more precise definition in science. Science defines acceleration as the rate at which velocity changes. Recall that velocity describes both the speed and direction of an object. A change in velocity can involve a change in either speed or direction, or both. So in science, acceleration refers to increasing speed, decreasing speed, or changing direction. Okay? We think of it just us. Acceleration means something is speeding up and going faster. Science has a different definition to it. Yes, Caleb?
There are some very high-tech cameras that can go way more than 50,000 frames.
Yes, I'm well aware of that. Yeah, you got some that can do up to like 240 frames per second. Yeah. Okay. And they can catch all kinds of really cool stuff. And we will, in fact, as we go through this book, we will watch some various films and things where they have used those cameras and slowed things down. Okay? So increasing speed. Whenever an object's speed increases, the object accelerates, obviously. A softball accelerates when the pitcher throws it, and again when the bat hits it. A car that begins to move from a stop position or speeds up to pass another car is accelerating. People can accelerate also, just for example, if you accelerate when you coast down a hill on your bicycle. How many of you still ride bicycles and do that? Yeah. As you go down that hill, if you don't brake and you just hold on for dear life, and this is steep enough hill, you will pick up quite a bit of speed going down that hill, right? Yeah, that used to be so much fun when I was a kid. I just love to do that. Then you find out that the brakes on your bike doesn't work, and you're like, oh. And then you start trying to make the short turn, and your bike goes out from under you because of loose gravel, and you fall down. Yeah.
That happened to me
It
whenever
just
I was
gets
going
ugly.
down. I
All
was
right.
going down a steep hill and then my chain.
Now, decreasing speed, just as objects can speed up, they can also slow down. And this change of speed is sometimes called deceleration, okay, or negative acceleration. Okay. For example, a softball decelerates when it lands in a fielder's mitt. Okay. A car decelerates when it stops at a red light. A water skier decelerates when the boat stops pulling him. Okay. All of those are examples of them slowing down. Changing direction now. Even an object that is traveling at a constant speed can be accelerating. Okay, you wouldn't think so, right? If a car is going down the road at 55 miles an hour and it's maintaining 55 miles an hour, you don't think of that as that car accelerating, right? But it is. Okay, because recall that acceleration can be a change in direction as well as a change of speed. Okay? So therefore, a car accelerates as it follows a general curve in the road or a lane change. Okay? Runners accelerate as they round the curve in a track. A softball accelerates when it changes direction as it is hit. Many objects continuously change direction without changing speed. The simplest example of this type of motion is circular, okay? Or a motion along a circular path. For example, the seat on a Ferris wheel accelerates because it's moving in a circle. Now that doesn't mean that it's actually speeding up and then slowing down, and speeding up and slowing down. It's constant, but because it is moving, it's changing direction, so therefore it is considered acceleration in science. Yes, Caleb?
I watched this video and they were able to frame lightning striking.
It's pretty cool.
Pretty cool.
You watched the video where lightning was striking because of the slow motion camera. We're still on. Yes?
What page are we reading, like, till the end of this chapter?
Maybe. Don't want me to ask you this question.
We started on page 22,
Yeah.
and we're now on page 24. We're getting ready to start 24 now.
Oh,
Are you asking if we're going to the end of the chapter?
yeah.
That's kind of the plan.
Okay.
But we're going to continue with some more on acceleration tomorrow. That's why you don't have homework tonight.
Yeah.
I've got a plan, and I've got it accelerated in high gear. Okay. And then as I hand out your homework tomorrow, it will decelerate as it lays on your desk. All right. Now, calculating acceleration. As we read this, if you're not careful, you're going to end up scratching your head going, wow, that sounds so complicated, and it's really not. So before you start panicking and thinking, oh my gosh, I don't understand what this is saying, don't worry about it. We're going to explain it. Okay, it's pretty simple. Acceleration describes the rate at which velocity changes. If an object is not changing direction, you can describe its acceleration as the rate at which its speed changes. To determine the acceleration of an object moving in a straight line, you must calculate the change in speed per unit of time. This is summarized in the following formula. So the way to find out what acceleration is, the formula is you take the final speed minus the initial speed divided by the time it took to cover point A to point B. Now that sounds really complicated, or a lot of steps that you might let something fall through the crack. It's really not, okay? We're going to talk about this a little bit better. If speed is measured in meters per second, okay, that's the M/S, and time is measured in seconds, the SI unit of acceleration is meters per second, or M/S squared. Okay? And you got to always make sure you put the square, the little 2, the exponent up there. That means it's squared, okay? What happened if it had a 3 by it? What's that? Cube. Yeah. What happened if it had a 10 by it?
To the 10th power.
To the 10th power. There you go. Very good. Okay. Now, suppose speed is measured in kilometers per hour and time is measured in hours. Then the unit for acceleration is kilometers per hour, or kilometers/hours squared. Okay, so it's not that hard. It sounds kind of like, what are they saying? But it's really quite simple. Yes?
What is initial speed?
Initial speed is what you started with.
So 0.
Well, depending on when you started timing.
Oh.
Yeah, if somebody didn't start timing you until you pass a certain point, and then they timed you to another point, you might already have some speed going. So you know, but yes, a lot of times the initial speed would be 0. You're absolutely correct. Okay? Yes, sir. Okay? So to calculate the average acceleration of the airplane, if you look up at the top of the page there, you must first subtract the initial speed of 0, because the plane starts off setting still, okay? And then you have to you subtract that from the final speed of 40 meters per second, okay? And then you divide how long did it take him to get to 40 meters per second. And it took him 5 seconds. So 40 minus 0, of course, is 40. Divided by the 5 would be 8 meters per second squared. Right? So he covered, if you look at that picture, every 1 second, he covered an additional 8 meters per second. So he started out at 0, went to 8, went to 16. At 3 seconds, he's at 24. At 4 seconds, he's at 32. And at 5 seconds, he's at 40. Okay? So that's what that's calculating out. Okay? For those of you sitting here not paying a lick of attention, this is going to be on the test. Problems like this is going to be on the test. Just so you know. Okay? All right. So the airplane accelerates at a rate of 8 meters per second squared. This means that the airplane's speed increases by 8 meters per second every second. Okay? Now, we'll take a look at some more of the calculations. As the roller coaster car starts down a slope, its speed's 4 meters per second. But 3 seconds later, it's at the bottom and its speed is 22 meters per second. What's the average acceleration? Okay, how do we figure that out? What do you do?
So the initial speed is 4, and then the final speed is 22. So then you'll subtract 22 and 4, which will equal 18. And then you divide that by 3, which will equal 6. So it'll be 6 meters per second squared.
There you go. That's it. Very simple. No clue. Okay, so the initial speed was 4 meters per second. The final speed was 22 meters per second. So you subtract 4 from 22. That's 18. It took 3 seconds to cover that distance. So you would divide 3 into 18, which means he was moving 6 meters per second squared. Okay? It's really not all that hard. Yes, Caleb?
And I guess, you could also do it at different times in those 3 seconds,
Yes.
Yeah.
Yeah. Well, it's kind of like, let's do the one, this one doesn't work it out for you. Over here where it says math practice, calculate acceleration. A falling raindrop accelerates from 10 meters per second to 30 meters per second in 2 seconds. So what's the raindrop's average acceleration? What do you think?
So you would
Add,
Hold up, I got somebody answering.
you would add the 10 and you would subtract the 10 from the 30,
Yeah,
and then you would divide it by 3,
like 2, yeah, 2 seconds.
5,
So
or no,
if you take 10,
It'd be 10 seconds.
30 minus 10 is 20, divided by 2 is 10. So you were going 2 meters per second square.
10.
10
Can I
meters
say
per
2
second
or I
squared.
meant 10?
There you go, 10 seconds per meter squared. Okay, the other one here,
math problem.
you've got a certain car can accelerate from rest to 27 meters per second in 9 seconds. So what is his average? Oh, now you messed up. What is his average acceleration? What is it?
3 meters per second.
Yeah, it'd be 3 meters because he was sitting still. Took him 9 seconds to get up to 27 meters per second. So 27 minus nothing is 27 divided by the 9 is 3. See, it's really quite simple. It's not that hard at all. Okay? What we got it here? 15. Okay, cool. All right. Now the other one is grafting. Again, we're not worrying about grafting so much because that is a little bit higher. But if you'll notice, the way you graft something, we've talked about this 2 or 3 times already this year. You take it and you put your dots when you're at a certain time or a certain speed or whatever. Then you put your dots on the graph and then you connect them. And if somebody is just timing you, yes, you get the same results. But if you graft it out like this, especially if it comes to if you rest somewhere along the line or something like that, then that helps because it shows the rest area and then to start back up. And that's what graphs are used for. Now they're talking about just riding a bicycle down a hill, just because you are 6th grade and they're trying to put it on something that might hold your interest for 2 seconds. But it's just about suppose you ride your bike down a very long steep hill. At the top of the hill your speed is nothing, but as you start down that hill your speed increases, and every second you move at a greater speed and travel at a greater distance than the second before. Okay? So during the 5 seconds it takes you to reach the bottom of the hill, you are an accelerating object. Okay? And by grafting it, you can kind of show what that is. Okay? Again, we're not going to work these kind of math problems on the test. I'm going to leave that so when you get into algebra, so you start worrying about sloping and stuff like that. But just kind of, if you do pay attention to it, it probably would help you a little bit. It's not that complicated. You just got to know where your X and Y axis is and where to plot it, but it would give you all the information you need to do those types of problems, okay? All right. It's about a 19.5-minute video. There we go.